When interpreting graphs of position versus time or velocity versus time, here's the most important point. In those graphs, the slope means something. In a graph of anything versus time, it turns out that the slope is just equal to the rate of change in that thing. Let's look at a graph of position versus time, where slope would then mean the rate of change of position. Oh, here's the graph, and slope, of course, is the change in the vertical variable divided by change in the horizontal variable. How much change in the vertical variable do you get per 1 unit of change in the horizontal variable? And remember that you calculate slope just by picking 2 points on the line, and then you look at their the vertical coordinate and the horizontal coordinate of each point. Here's at time initial, there's the initial location, and at final time, a later time, there's final location. And so then slope is just change in the vertical variable, change in location, divided by change in the horizontal variable, change in time in this case. I can write change in position, also known as displacement, this way, and for shorthand, and write change in time for shorthand this way. Remember, the delta always means change in whatever follows, and the change is always the final value minus the initial value. But this quotient here you've already seen. It's just our definition of velocity, which makes sense because velocity means the rate at which position is changing. Velocity is the rate of change of position. So a graph of position versus time, the slope would give you the rate of change of position as time goes by, but rate of change of position is just another name for velocity. Put that idea into a slogan that's easy to remember, and we have this. Anytime you have a graph of position versus time, in any graph of position versus time, the slope is the velocity. Slope is velocity. This symbol here just means this thing implies this thing. That is, if the thing to the left of the arrow is true, then the thing to the right of the arrow must also be true. Slope is velocity in a position versus time graph. So let's look at a couple examples of that. Here's a graph of position versus time, and from the time that goes here to here, you've got one constant slope, so that means one constant velocity. Same slope from this time to this time. Since slope is velocity, then anything you say about velocity, you can say about slope and vice versa. Constant negative slope, that means constant negative velocity. So we would draw that part of the velocity graph that way. But the location is always becoming more negative. Or to put it another way, there's motion in the negative direction. The location at a later time is always more negative than location at an earlier time. So if you have this more negative number minus this less negative number, that's always a negative change in location, always a negative displacement. And here, from this time to the end, you have a constant positive slope. That means a constant positive velocity. Anything you say about slope in a position versus time graph is also true about velocity. So there. And notice that the absolute value of this negative velocity, I've drawn this graph so that the absolute value of this negative velocity is the same as this velocity. Usually we think of speed as just the absolute value or the magnitude of velocity. So these two things have the same speed. That this might be negative 4 meters per second, then this would be positive 4 meters per second. Because of the symmetry here, we see that these two slopes are equally steep. The rate at which position is changing is just as fast here as it is here. The only difference here, the change is negative, and here the position is always becoming more positive. The change is positive. Let's look at a second, slightly more complicated example. Here's the position versus time graph. And so the velocity versus time graph would look something like this. Let's line up the times where the motion changes. Here, it's a horizontal line, so the slope is 0. Slope is velocity, so velocity is 0. Or to put it another way, during this time, the location stays the same. The location stays the same is just another way of saying that the object is not moving. So no velocity. Here in this time interval, the slope is constant and positive. That means constant positive velocity. And then during this time interval, again, just like here, the slope is horizontal, so the slope is 0. 0 slope on a graph of position versus time is the same as saying 0 velocity. Once again, the object is staying at the same location for all those times. In other words, it's not moving. Then in this time interval, slope is constant and negative, so velocity is negative. Position is always becoming more negative. That means the motion is in the negative direction. And I'll draw it like that. Constant negative velocity. And then here, again, 0 slope means 0 velocity. Staying at the same location for all this time means 0 velocity. Notice, for this negative velocity, I made the absolute value of that negative velocity less than this. That is, in this time interval, the speed is higher, and in this time interval, the speed is lower. That's easy to see in this case because in both cases, the total distance traveled, here's the location at the start, here's the location at the end, so this much distance traveled is the same distance traveled over here. Just the only difference is that here's the start and here's the finish. But in this time interval and in this time interval, the same distance is traveled, but in this case, the object moves through that distance more quickly in less time. Here, it takes more time to travel that same distance, meaning it's slower. The absolute value of its velocity, in other words, the speed, is less. Remember, speed simply means the magnitude or the absolute value of the velocity. It's what tells you how fast the object is moving without regard to the direction of motion. We also see something else here. Because slope is velocity in a position versus time graph, it also turns out that steeper slope always corresponds to a higher speed. Gentler slope always corresponds to a slower speed. And we see an example of that here. Here's the steeper speed, here's the steeper graph. It had the higher speed. Here's something with less steep slope. It moved with the lower speed. It took longer because the fact that the slope here is gentler, not as steep as it is here, is because during this time the same distance was traveled, but it took longer to travel that distance. That means the object was moving slower, and it also means that the slope of this line is less steep, more gentle than this slope. Steeper slope means faster, gentler slope means slower. Now, with this idea, we can work in the opposite direction as well. If we're given a graph of velocity versus time, from that we can deduce what a position versus time graph looks like, because in the position versus time graph, slope is velocity. So let's see how that works. Here's the velocity graph. Start out with a fairly slow positive velocity and then suddenly speed up to a new higher velocity, and you maintain that velocity for a little while. And then suddenly stop and turn around and move in the opposite direction with the same speed that you had here. What would a position versus time graph look like? A position versus time graph that is consistent with this velocity graph, that corresponds to this velocity graph. Well, remember what this is. This is velocity. On the position graph, slope is velocity. That means this graph tells you what the slopes are on this graph, because velocity is slope of a position graph. So here in this first time interval, velocity is small but constant and positive. So slope is small, constant, and positive. Okay, something like that. Small velocity means small slope. Again, less steep slope means slower. Now all of a sudden you speed up to a higher velocity. So now again positive velocity, constant, but bigger than in the first time interval. Something like that. And then in the third time interval, constant negative velocity, but the absolute value of this negative velocity is the same as this velocity. In other words, the magnitude of this velocity is the same as the magnitude of this velocity. In other words, they've got the same speed, just moving in the opposite direction. So same speed means that this line must be equally steep as this. Just now this one has a negative slope, but just as steep as this. Something like that. Now, here's the trick. This isn't the only position graph that is consistent with this. This tells you the slopes, but this doesn't tell you anything about the locations. So the moving object could be going through different locations, it could be located at different places, but as long as it has this speed, and then this velocity, and then this velocity, it's a kind of motion that is consistent with this velocity graph. So this velocity means a particular slope on this graph. So anything, any position graph that has this slope, then this slope, then this slope will be a position graph that is consistent with this. For example, that the slopes in these 3 time intervals are the same as the slopes in these 3 time intervals. And since on this graph slope is velocity, that means the velocities here are the same, even though locations are different. The velocity in this time interval is the same, even though the locations are different. The velocity in this time interval is the same, even though the locations are different. Same slopes for those different position graphs, and since slope is velocity, that means they all have the same velocities. So, slope is velocity in a position versus time graph. Now, the word slope, the concept slope, is something that applies to straight lines. What if the position line in a velocity versus time graph is not straight, but curved instead? Something like this. We can still say that in this position versus time graph, just like every other position versus time graph, slope is velocity. But now, when the position line is curved, slope means something a little bit different. Imagine that you want to find the slope at one particular moment in time. Say this time here. We'll call that time capital T. And now go up to the point on the position curve for that time, the location for that particular time, and then draw the straight line that is tangent to the curve at that time. A straight line that is tangent to a curve touches that curve at only that point. So it would look something like this. Now that's a straight line, and the slope of that straight line is the velocity at time capital T. And that's the idea. But notice on this position versus time graph, because the position line is curved, slope changes, or the slopes of the tangent lines are different everywhere, which means velocities are different everywhere. Here, at this time, let's call it T1, the straight line that's tangent to the position curve at time 1 would look like that. It has a steeper slope, a larger slope than this slope, but since slope of the tangent line is velocity, this slope is bigger than this slope, so the velocity at this time is greater than the velocity at this time. And in fact, Sorry, the computer's acting up a little. On this curve, because it's a curve, the slope of the tangent line is different everywhere. It's always changing from time to time. Slope of the tangent line always changing means velocity is always changing. Or to put it another way, if the position line is curved, that indicates changing velocity. And if the position line is not curved, that indicates not changing velocity, constant velocity. Straight lines on the position versus time graph mean same slope everywhere in that time interval, so constant velocity. Curve means changing slope of tangent lines to be specific. Changing slope means changing velocity. And again, we see that steeper corresponds to faster, and less steep corresponds to slower. I just start this over again to make that a little bit more clear. So compare the velocity at t1 to the velocity at capital T. So at t1, there's the straight line that's tangent to the curve at that point. At time capital T, there's the straight line that's tangent to the curve at that point. Now, imagine that if this slope had been, say, a constant velocity during this much time, then the object would have moved from here to here. Right? The object was here at an earlier time, and it was here at the end of this time interval. So it moved this far in this time interval if it had had this constant speed for that whole time interval. Now do the same thing for this. For a time interval is of the same size, at the beginning of that time interval, this was the location, and at the end of that time interval, this was the location. So in other words, if right around this time the speed had been just the same as the velocity had been just the same as the slope of this tangent line for that whole time interval, then the object would have moved from this location to this location. It would have traveled this distance, which is a much shorter distance than this. In other words, where the slope is steeper, the object travels a greater distance in a particular amount of time, and where the slope is gentler, the object travels a much shorter distance in that same amount of time. In other words, it's slower. So everything that I've said here is really is nothing but a consequence of the fact that in a position versus time graph, slope tells you the rate of change in position, which means in a position versus time graph, slope is velocity. Everything else is just a consequence of that important idea.